Hi, everybody. Welcome back. So last time we talked about amplitude amplification and showed how you can end up boosting the probability of success for some sort of any quantum protocol you feel like, really. And we use that in order to be able to show that we could get a quadratic advantage for solving the search problem. So today I'm going to spend a little bit of time elaborating on what we covered last time to show specifically how we can use this in order to be able to boost the probability of success, and also a little bit of a discussion of what it means to have a good probability of success. Because with amplitude amplification, not all probability of successes are actually created equally. So let me share my screen and we can jump right in. So if you recall, the basic idea behind amplitude amplification is that we considered a walk operator, which was of the form minus, that minus is really just there for aesthetic purposes, but is equal to minus identity minus twice the projection onto the initial state, which I guess I should write, to psi over here, and another reflection that reflects about a good space over here, which is the set of all states that we want, where if the state is in psi is in good, then this projection acting on the state psi will just give us back the state. Okay, so that's what the role of the projection is. Again, the projection checks to see whether or not our or finds the component of our state in the direction of the good subspace. And this over here, of course, just reflects about the good subspace. And so the idea, basically, if you recall, is that we had this kind of geometric picture of what's going on. We have an initial state up here with some angle theta, and this state up here I'm going to call psi g, and this one I'm going to call psi b, for the good and the bad projections of our initial state psi. And we showed last time that when we do this protocol, everything only stays within a two-dimensional space. So it suffices in general only to look at psi g and psi b. And then we found that if we apply, every time we apply w, right, what will happen is this would be w psi, which would be 2 theta over here. And w psi again would be another 2 theta. This would be w squared psi up there, and so on and so forth. And so in general, this formula just from geometry gives us wp acting on psi is equal to sine 2p plus 1 theta psi g plus cosine 2p plus 1 theta psi b. And this implies that the probability, if we were to measure and to see whether or not we're in the good space or not, and the way that we could measure this would be just by doing the Hadamard test. So a Hadamard test circuit would involve something like this. I minus twice the projector onto good. H measure. Here we start with 0 and we have psi down here. This is how we could measure the probability of success, that this 0 up here, I guess, will be 1/2 plus half the probability of success from our previous analysis of the Hadamard test. So, okay, cool. Bit of a digression, but let's get back to it. Probability of success then will end up being just sine squared 2p plus 1 theta. Okay, cool. So let's take a look at the two special cases, right? Let's take a look at the case where probability of success initially, so this would correspond to p equals 0, is just by definition sine squared theta. Okay, and if the probability of success to begin with is equal to 1/4, then let's figure out what theta has to be. Theta then is just going to be the arcsine of 1/2. Now, this is a very special angle. The arcsine of 1/2 actually is equal to pi by 6. So just like, just like all of your teachers you probably run into before, right? When they're giving an example of something in trig, it always boils down to rigged numbers. And this is a fantastic rigged number. It's pi by 6. So let's plug that in. Well, the probability of success after applying WP times now is, as we said before, sine squared of 2p plus 1 theta. Now, theta for this particular case is pi by 6. So this is sine squared of 2p plus 1 over pi by 6. And I think you can start seeing what will happen here. Let's put in p equals 1. And in this case, the probability of success ends up becoming sine squared 3 pi by 6, which is equal to 1. So for something that has a 1 in 4 probability of success, a single application of amplitude amplification will boost it up to 100% probability of success. Okay, now let's take a look at a different case. Case 2 would be the probability of success initially when p equals 0 equals 1/2. Now this feels like a lot better of a case, right? Because we got twice the success probability that we had in the case of 1/4, but we'll actually see that it's far worse. The reason why is that in general, if this probability of success is equal to 1/2, this is equal to sine squared theta. So this implies that theta is equal to the arcsine of 1 over root 2, which is equal to pi by 4. So geometrically, if we take a look at this, what we see is we see a situation like this. We've got an initial state where this angle is pi by 4. Okay, now let's go through and figure out what happens. Well, the next operation is going to increase that angle by 2 theta. That's this and then that. So we'll go to an angle out here where this is pi by 4, and in turn, that's pi by 4. So the probability of success geometrically is going to exactly be the same as it was before. Now, if we do this one more time, this would be W psi. Now, when we apply this twice, we can see geometrically that we'll get the same situation, just now with a negative component. And similarly, this will be W cubed psi. And there you have it. You see that at every point, the probability of success, which is the magnitude squared of the y component of this kind of butterfly-like thing with a horrible way I've drawn it, this probability of success squared is always 1/2. Algebraically, we can actually take a look at this and say, okay, well, sine squared of 2p plus 1 pi by 4, this is equal to sine squared yeah, well, I guess it's always going to be 2p, or sorry, it'll be p times pi by 2 plus 1/4. And we can end up seeing, because, plus pi by 4. And we can end up seeing, just using standard trig identities on this, that this is always equal to 1/2. Okay, so that is how we run into this weird problem, right? Where the probability of success is actually always going to be 1/2, no matter how many times we apply amplitude amplification here. So how can we end up making this work? Well, the idea is that we redefine success. So let's say what we have is, I'm going to define a oracle over here. Let's define an oracle OG. And OG is going to have the following property. OG acting on x0 equals x1 if x is in good, and it will give me x0 otherwise. So this actually kind of ends up giving us a bit oracle that corresponds to our phase oracle that we had for our reflection. And in particular, the operation identity minus twice the projection onto 0. This actually can be thought of as the following circuit. If it can be thought of as taking a state psi as input, feeding in this into the good oracle, keeping a bit that stores whether or not the state is good. So this is now will be 1 if psi is in good. Then what we can do is we can apply a Z gate to it and apply our good oracle again. And this will end up giving us our reflection. Okay, so this is an oracular way that we can think about the problem. Now, obviously, for any particular example, we would need to break down and figure out how to implement OG. But since if we want to talk about this at a high level, all we need to do is just posit that somebody's created an operation that has this role. So this is what we're going to have. And now our probability of success that we ended up getting for this is P of success is equal to 1/2 when we're considering our measurement. So what we would like to do is we would like to be able to turn this OG, right, into an OG that will end up flagging half the probability of half the states. Now, the reason why we want to do that is that we saw that probability of success 1/4 is awesome, because with probability of success 1/4, at a single operation or application of amplitude amplification, we can boost the success probability to 100%. If the initial success probability were 50%, on the other hand, no number of applications of amplitude amplification will work. So if we know that we have a 50% success probability, then our goal is to lower it down to a 25% success probability. And the reason why I'm introducing OG is that I want to be able to give myself enough freedom so that I can manipulate the success probability in order to actively lower it down to 1/4. Once it's at 1/4, then I can use this trick in order to boost it back up. Okay, so in order for us to purposefully lower the success probability, the way that we can do that is as follows, right? We have a state psi coming in the top. Now we feed that into OG over here, and this contains a value 0. Now I'm going to add an additional quantum bit, and this quantum bit is going to actually serve no purpose whatsoever other than to allow us to selectively lower the probability of success. So we're going to put a state 0 through here, and I'm going to do a Ry of 2 theta operation on here. Then I'm going to have a third qubit. So we've introduced 2 new qubits here. And then I'm going to do a Toffoli gate now down between those 2 and implement our Y dagger of 2 theta here. Then I'm going to query OG again at the top. I'm sorry, there's only one line coming out of that rotation. And then this is going to allow us to selectively reduce the probability of success for the circuit, where we measure the probability of success. This is going to be equal to the probability that this is equal to 1. Okay, cool. So let's just go through the quantum state and take a look at what that probability is going to be of this being 1. So applying our first quantum operation, we end up getting psi goes to, after OG, we can end up writing this as just the sum over all x. Or I guess, yeah. OG is going to allow us to write their state in 2 different spaces. It's going to allow us to write our state as sine theta psi G1 plus cosine theta psi b 0. Okay, so now that we've got this state, we've also got, of course, the other ones off to the side, which are 0, 0. Now I'm going to do a rotation. I called that theta. I'm really sorry about that. Let me call it phi, just to make sure that we don't get confused between the success probability, which was sine squared theta by default, and this controllable angle that a user can just choose to set to be anything they want to lower the probability. Okay, now if we carry out this rotation, what we'll end up getting is we'll end up getting sine theta psi g 1 plus cosine theta psi b 0. Now the ry of 2 theta is equal to, again, cosine theta identity minus iy sine theta. And so this, when we apply it to the 0 state, will give us cosine theta, or phi acting on 0 plus sine phi acting on 1. Okay, so now let's go through and do another operation on this, which is the Toffoli. The Toffoli is just going to flip this last bit I failed to draw here, in the event that we end up getting 1 here and 1 there. And so this will end up giving us sine of theta sine of phi 1, 1, 0 plus some other state that I'm, 1, 1, 1, plus another state, I'm gonna, with amplitude 1 minus sine squared theta sine squared phi. That's perpendicular to it. I don't want to go through the details of this perpendicular state because this is the only state that's ever going to, this is the only component of the vector that's going to have an amplitude that when we measure this probability of success down at the bottom is ever going to give us a value that's non-zero. So let's just take a look at, if we take a look at this, right, we can immediately see that the probability of this qubit being 1 over here is going to be sine theta squared times sine phi squared. So the probability of this is, this being 1 is equal to sine squared theta sine squared phi. Okay, so this means that if we use this particular circuit, then in effect, theta, we have that sine squared theta maps to sine squared theta sine squared phi, where the user can, again, always pick what that angle phi is going to be without loss of generality. And I'll call this angle, I'll call this sine squared theta prime. Okay, so this angle theta prime, which corresponds to the effective new success probability of this entire circuit, is now going to be the square root of sine squared theta sine squared phi, which is, it is going to be the arc sine of this. And this is, of course, going to be the arc sine of the sine squared theta is just the probability of success. So it's going to be square root of the probability of success times the absolute value of sine phi. Okay, so now let's take a look at the case where we're looking at 1/2, or p suc is equal to 1/2. What we would like to do is we'd like to be able to change the value of theta prime corresponding to this success probability, because this is, if we now consider doing amplitude amplification with this implementing our projector, let's call it PG prime, then our new walk operator, W prime, corresponding to this, will be of the form identity minus twice projection onto psi tensor 0 for those extra bits that end up getting included, and then multiplied through, let's put a negative sign in for purely aesthetic reasons, 1 minus the projection onto good prime twice, where this operator that we discussed over here implements our oracle that ends up checking to see whether or not we're in a good space. And then once we have that, then we can turn that into a reflection pretty straightforwardly just by using this construction. So, oh, sorry, I called it PG prime. Really, let's call this OG prime for the new version of the G oracle that that corresponds to this lowered success probability. Okay, so that's the basic idea of what we want to do. So if we've got the success probability from this new walk operator, we end up finding that this is going to be the arc sine of square root 1/2 times the absolute value of sine phi. Oh, and we would like this to be equal to 1. Or sorry, we'd like this to be equal to 1/4. And so the way that we can end up doing this is we can just actually, or sorry, this isn't the probability of success. This is the angle that we want. And we would like the argument inside all of this to be equal to 1/4, meaning that what we would like, that's strange, it wouldn't erase, is we would like 1/4 to be equal to 1/√2 times sine phi in absolute value. So, or I should say actually sine squared here, and that is equal to 1/4. So therefore we want sine squared of phi equals 1/2, and therefore it suffices to take phi equals pi/4. So for example, we could have actually just, instead of using an RY gate here to lower the success probability by 1/2, unsurprisingly, we could have just applied a Hadamard gate. And that makes perfect sense, right? Why it would lower the success probability by 1/2, because imagine we've got a good state up here. The only way that this Toffoli gate will trigger is if we have a good state and this coin, you can think about the state as like a coin that we're flipping. And if this coin with some particular bias specified by phi ends up coming up as 1, then we mark the state as being good. And so this is what allows us to purposefully reduce the success probability, because we're only now counting a success to be a success up here and a success down here. And so we can use this circuit to actually lower our success probability to anything we feel like. And that is the key trick. So the key trick then is the key question is, how do we make all of these guys deterministic? This is kind of strange here. I don't understand why there's text everywhere. Huh. Okay. Okay, sorry, what? All right, this is beyond strange. Sorry for the technical problems. What the heck? Oh, PowerPoint, how I love thee. So maybe I'll need to find another product for this. But let me just overwrite one of my presentations that's open in one of my infinite tabs. Okay, so basic idea then is that we've got some probability of success. We have our probability of success in general. We can actually amplify to 100% probability of success only for some very particular values. And so the probability of success at P, as you recall, is in general, if we've got some angle theta, and I'll call it theta prime to refer to the augmented probability or the lowered probability that we had before. Okay. And if we want to have this equal to 1 for some P, then it suffices to pick theta prime equals pi over 2q plus 1. Okay. Or I guess I should say, let's make it p plus 1. Then at p iterations, the amplitude amplification will boost the success probability up to 100%. And so this ends up creating some values. Okay, so I'll call these like the magic angles. So theta magic set of these guys would be 0, pi by 6, and a whole bunch of other values. So the basic idea is that what we would like to do is we'd like to say we've got a value of theta, right? And in general, what we'll find is that we'll have theta magic sub q for some, or sub q for a particular case is going to be less than or equal to, or greater than or equal to theta prime, which will be greater than or equal to theta magic sub q plus 1, right? Because this is a decreasing sequence, or actually, I guess it's in, oh no, I'm sorry, I did this wrong. Theta magic, that was the value p. Theta magic, the first component is pi by 2, not 0. So this is a decreasing sequence of angles. So what we would like to do is we'd like to be able to say, if we've got an angle theta, then we're going to choose to round down to the next sequence over here. So what we need then is we need theta prime has to be equal to pi over 2 to q plus 1. Okay, now theta prime is the arc sine of the square root of the initial probability of success times sine squared phi. So this implies that sine of pi over 2 times 2q plus 1 squared let me just make sure that I'm doing this right. Oh, it shouldn't be sine squared. I think it should be the absolute value of sine. There we go. So we take take that. Actually, I guess I don't need to do that. I need to just take the sine of this, divide this through by the square root of the probability of success. And this is going to be equal to sine phi. And so we can invert this by saying that phi is equal to the arc sine of sine pi over 2, 2q plus 1 divided by the square root of the probability of success. Okay. And that will end up giving you the angle that you need to use in the previous circuit that I showed in order to boost the probability of success to 100% for some value of it. So this will allow us to make amplitude amplification always work, provided that we know what the probability of success is before we started. All right, so you might ask, okay, well, how do we boost the probability of success? Or how can we apply this idea of amplitude amplification in cases where we don't know the probability of success? Because in most of the reasonable cases that we're taking a look at, we won't actually know how to do this. And the basic idea is actually really kind of straightforward. And it's analyzed in both the textbook as well as in the kind of seminal paper that introduces the idea, amplitude amplification and estimation by Broussard, Tapp, Hoyer, and Mauska. And so the basic idea behind this is it's actually a randomized classical algorithm for finding a good state. And here's how the algorithm works. The algorithm says for p equals 1 to infinity, do the following. Prepare state psi, apply w to the p minus 1 on psi, measure p good, meaning, try to measure the state and determine whether or not it's in the good space. If in good, then break. I'm sorry, actually, this isn't quite right. What I mean is actually, I mean to the 2p minus 1. Okay, now this looks really scary, right? Because you've got an exponentially increasing size of the rotation. And so the probability of success that we end up getting at every value of this iteration would be probability of success of 2p minus 1 is then going to be sine squared of 2 to the p minus 1 of whatever our initial theta is. So geometrically, this is what's happening, right? We go through and we have, say, some tiny rotation through an angle theta. Okay, we do a single iteration, which will move us up 2 theta. We'll measure, and if that worked, great, we found an example. If it didn't, then we're going to try again. And this time, what we're going to do is we're going to now double the size of the rotation that we used before. So we're going to apply 2 iterations. And so this is going to now be grand total of 4 theta. Then if that fails, when we measure up here, we're now going to amplify again and double our angle. And now this is going to be 8 theta. Okay, so on and so forth until we finally end up succeeding. The cost, which is the number of W's that we end up needing, this is just going to be the sum from p equals 1 to p final of 2 to the p minus 1. Which, because of the fact that this is a geometric series where the size is doubling every single time, this is in the order of 2 to the p final. Okay, so the cost of doing all of these steps up until the last one that you did, it all adds up at most to a fraction of the cost that you end up doing in the last one. And so what that ends up meaning is that kind of, to a good approximation, all of those steps you did before you ended up getting to the success, they're asymptotically negligible in terms of their overall cost. And in fact, there's only a logarithmic number that you end up needing. Okay, So that's cool. But why does this, in terms of the value that you're going to need for P final, it's not guaranteed, but you can do statistical analysis of this. And the value that you end up needing for P final is with high probability on the order of square root 1 over the initial probability of success. Okay, which is exactly what the cost that you would expect from ordinary amplitude amplification if it was deterministic. Okay, and the reason why this ends up working basically is that once you've gone up to this point where we're doing these big rotations, right? Then, okay, I guess let's do the next one past this. I did 8, right? So now 16 would be kind of more like this. And now 32 is just going to lead to the situation where the vector is now spinning around wildly, many times conceivably, okay? Now the final angle that you end up getting, or the final probability of success when you repeat this, it averages out to a probability of success that ends up being about a half. So once we get to the point where it's spinning around like crazy, the probability of success, i.e. the y component of each of these vectors over here, on average in magnitude is about half. So what that ends up meaning is that every time we increase, we've got a constant probability of just ending it. And so there only ends up getting to be a logarithmic tail that we end up getting in order for this process to succeed with high probability. So when we consider that and go through the average, we see that because there's an exponentially shrinking probabilities for for having failed enough times to just keep on spiraling, that the total cost when we sum everything ends up basically just adding up to a constant factor times the cost that we would have when we end up ending at the exact point that we would ideally want. So that is how we can end up boosting the success probability to, well, not boosting the success probability to 100% in this case. This shows a non-deterministic algorithm that will end up providing us a good state with high probability using the same number of queries asymptotically that we would end up needing in order to be able to do this in the case of amplitude amplification where we do know the success probability. So it gives you a way of doing it. So the moral of the story is that you don't need to know the success probability in order to make amplitude amplification work. However, you need to know something about the success probability in order to be able to get it to work deterministically. Okay, so that is amplitude amplification in a nutshell. I want to emphasize how important this algorithm is. Well, search is a particular example of it, and actually a rather fairly maligned application of amplitude amplification. This technique is insanely powerful. The majority of quantum algorithms that are used right now will use some flavor of amplitude amplification to improve at least one part of it. So understanding and applying amplitude amplification, it's a real art in and of itself, but once you master it, you really actually get this ability in order to be able to do a whole host of things that otherwise in quantum computing would be really challenging to get a quantum advantage for. So thank you very much. And I hope you stick around next time when we talk about using the polynomial method in order to show that techniques like this actually end up leading to optimal algorithms for search. All right, see you all next time.